Okay, so this much I already talked yesterday. Actually, I can start. Talking from this point. So the problem with level 0 is this strip structure. Although it is nice, as I said, if an application needs the data by sector, first get the first sector, second sector, third sector, fourth sector, etc. in sequence. This will not be any faster than A or B, level 0 or level 1. Will not be any faster than a single disk. So the solution is, instead of dividing my data into strips, let's divide them into bits. Okay, let's divide them into bits. So the data that you store in hard drive is divided into bits. Okay, your bit number 1 will be stored in this hard drive, bit number 2 here, bit number 3, 4, 5, 6. It goes like that. So even a single application needs a single sector. Okay, all of the data has to come from all of these disks. Okay, all of these disks. This is called RAID level 2. So RAID level 2, the difference between RAID level 2, 0 and 1 is 0 and 1 uses the strip structure. Okay, level 2 and level 3 uses the bit structure. Okay, bit structure. So why don't we use the bit structure RAID levels all the time then? If this one is always faster than this one, why don't we prefer them C and D over A and B all the time? Why do we need strips then? Some people prefer strips, even though it is a little bit slow for some cases, like the serial reading. But they say that we like the strips because, why? They say that strips are better for some cases. Any ideas? Any ideas? Reliability? What do you mean? Yasin, I mean, B is as reliable as, you mean in B there are backup strips, but look at D. Okay, level 3. There is a parity disk. So this one keeps the parity. If this one crashes, I can get that information from the parity disk. What is parity? You already know the parity, right? What is the parity of 0, 1, 0, 1? You just count the number of ones. If it is even and odd, okay? In this case, number of ones is odd, so parity will be 0. Okay? If your data is, okay, so it's like this. If your data is 1, 1, 1, and 0, the number of ones is even, so the parity is 1. So in this case, if one of the disk crashes, I can get that information from the parity disk. So I can provide the reliability with RAID level 2 and RAID level 3. There is something else. Any ideas? What is the advantage of RAID level 0 and 1 instead of, I mean, I could have C and D. I have other RAID levels like oh, sorry, I don't have it. So the reliability is not 1. I mean, I can provide the same kind of reliability with the bit structure too. So think about how you would build such a system. Okay, when you read data from this structure from RAID level 0, it is okay to have a little bit time difference between the disks, right? because you are reading different sectors. But when you come to this one or that one, you have to synchronize all of your hard drives perfectly, so that when one of them is reading bit number 1, the second one is reading bit number 2. So there should not be any time difference between reading bit number 1 and bit number 2, because they are going to part of the same byte, right? Same byte. So these two has to be synchronized very, very strictly. Synchronization has to be very carefully done. Okay, so that means that you need hardware help. You need hardware help for RAID level 2 and RAID level 3. For A and B, synchronization is not that important, because I mean, when you read strip number 0, let's say our K is 4. That means that if every sector is half a kilobyte, that means that strip 0 is 2 kilobytes long. Okay, while I am reading 2 kilobytes, I don't have to read it exactly at the same time the next strip. It could be maybe a few milliseconds later or earlier, doesn't matter. But in this case, for C and D, RAID level 2 and 3, I don't have such a luxury. Okay, Ilhan, did we start the attendance?
Not yet. I'm just doing it.
Okay, thank you. Okay, so a few examples. Level 0 has problems with applications that ask data sector by sector. We know that. Level 0 has reliability problems, but level 1 is more reliable. Still, level 1 has problems with applications that ask data sector by sector. Okay. For level 1, on a write, every step is written twice, but on a read, either copy can be used. Okay, so when you write a RAID level 1, you need to write it to 2 places. Okay, write it to this one and this one, both of them at the same time. But when you read it, you can read it either from this one or that one. So you may maybe distribute this reading order from one set to the other set to make the better use of your redundant disks. Okay, let's look at RAID level 2 and 3. Okay, 2 and 3, they do not use strips. Okay, they require all the drives to be rotationally synchronized. This is important. Rotationally synchronized. That needs hardware help. Both level 2 and level 3, they use error correction. Okay, if there is an error, level 3 uses parity, level 2 uses the Hamming coding. Hamming coding is a coding scheme. I think you know about this. That if there is an error during the communication, during the read-write, you can recover from that error using some calculations. Okay. Okay, so let's continue with our other RAID configurations. This is for RAID level 4, 5, and 6. Again, these are not using any bits. They are using strips. They don't have to synchronize rotationally the hard drives. RAID level 4 idea is kind of the same as RAID level 3. It uses the parity disks. Okay, there is a parity. So this looks like very similar to RAID level 0. In addition, I added this extra parity disk, RAID level 4. Okay, so if there is a crash, one hard disk crash, I can get the data from the parity disk. I know that. So what is the difference between E and F? Which one would you prefer? What is the advantage of F over E. Or what is the advantage of level 5 over level 4? They kind of use the same idea. So why would you prefer RAID level 5? Level 5, you mean? Level 5 is more reliable. Why? It uses 5 disks. The other one is using the 5 disks too. Both of them are using 5 disks. Their reliability is the same. Look at the... Okay, I can do the same thing with RAID level 4 too. I mean, if this one crashes, okay, I can get the data from parity. 5 separated amount of 5 separated. Yasin, I did not get what you mean. 5 separated among the strips. So Talai says that level 4 to get data from parities. Well, I mean, level 4 and level 5 do the same thing. They use both parities. Okay, they use both 5 disks, so their parity structure is similar. The number of disks is same. Eddie says that parity are distributed in level 5, so what? So Eddie, what do you mean? Everybody sees that parity is distributed. Why would that make a difference? Distribution of parity is why is important. If parity disk malfunction in 4, data can't be checked. No. Well, I mean, if parity disk is crashed, okay, I can the same is. I mean, if this one crashes, okay, I am in the same situation. There is no difference. By the way, parity disk is not used for checking. Okay, parity disk is there. If there is a crash, I have a way of recovering from. Level 5 is faster. Why? Why level 5 is faster? That's the right thing actually. Level 5 is faster because we distribute our data to 5 disks. I mean, where is the useful data? Useful data is here, okay? Useful data for me is here, 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 and here, okay? Only these 4 disks are containing the useful data. In this case, all five are them using the containing the useful data. So from time to time, there is a possibility that I am using all 5 disks to read the useful data. If there is something bad happens, of course, I need to do the same stuff. But for the good times, when I am reading the useful stuff, then most of the time I will be using all 5 of these instead of these 4. Okay, so both of them are using 5 disks, yes, but one of them is using 5 of them. One is using 5 of them for reading the useful data. Okay, so these are the kind of differences between the RAID levels. Okay. Yusuf says that RAID 5 can tolerate the loss of any single disk drive in the array. RAID level 4 can do that too, because I have the parity from the parity I can check what kind of bits I am missing. Instead of reliability, 4 and 5 is the same. 5 and 6 is faster than level 4. Okay. So level 6 is, it turns out that it is a little bit better in terms of reading. So these are kind of the differences between the RAID levels. As I said before, I wouldn't say level 6 is better than always level 4 because it is more complicated structure in terms of parities and etc. There are different configurations, and in Windows or in Linux you can set up many hard drives using this kind of RAID structure. They allow you that. Okay, so let's continue if there are no questions. Let's continue with disk formatting. Talai has a question: when in level 5 is crashed at strip 1? So she says that level 5 is crashed. Okay. Strip 5. Strip 1, strip. Okay, she says that if this one crashes, okay, if this one crashes, you cannot get data from P12, 15. Well, it is the same thing, Talai. If this one crashes, okay, if this one crashes, I am in the same situation. When one of the hard drive crashes, the system goes down. You need to go back up. You need to bring a new hard drive, and you recover all of your data from the other disks. Okay, from the other disks. So when you recover your data from the other disk and you install your new disk, you continue. So this is parity is about recovering your data. We don't mean that if this crashes, okay, if this crashes, I can continue without needing that disk. Of course, I need that disk. The thing is that when I install a new hard drive, brand new hard drive, I can fill in that disk from the information from other disks. That's what we are saying. Kamil has another question. Does RAID affect the random access speed or sequential data transfer speed? For the strip case, okay, sequential data is a little bit problematic. Why? Because, as I said before, if I read my data sector by sector, the strip structure doesn't help me. Okay, the strip structure doesn't help me. But if I read it, let's say 10 sectors at the same time, then it's going to help. If I am doing all the random access data, if I am doing all the random access stuff, and if I am reading a single sector, then RAID will not help me that much, because most of the time I will spend it in seek time, and seek time takes lots of time. So if you do lots of random access, you read a few bytes and you read another few bytes from the other end of the disk. That's not going to help me. No. Okay. So RAID is not always 5 times faster than the single disk. It depends on the application. So if the application knows that I have a RAID structure, maybe the application can change its behavior to ask the data in advance for the whole track. Maybe if I'm getting the whole track, then RAID is definitely faster. Okay, so let's move on and let's look at this disk formatting. Remember, again, I am going to draw my very primitive disk structure here. This is the center, and these are my tracks. Okay, and these are my sectors. They don't look very nice, but this is okay. So these are my sectors. So each sector usually, this is a sector. Let me mark this sector with green. Okay, this sector, if I bring it up like that, okay, it is 512 bytes, okay, half a kilobyte. Okay, when we buy a new disk, when we install it, there is nothing contained on this disk. Okay, and the disk doesn't know where the sector starts and where the sector ends. We need to format it. So how do we do that? Okay, we need to do the first level, low level formatting. We say that at the beginning of the sector and at the end of the sector, I have two special places. The first place is preamble, okay, and at the end I have ECC, and I have half a kilobyte of data in between. Okay, this preamble, okay, this preamble like that contains information about the cylinder and sector numbers. It contains information about cylinder and sector numbers. Anyway, my pen didn't work. Okay, so this preamble contains information about the cylinder and the sector numbers. I write that information in that preamble also. It also contains a certain bit pattern that allows the hardware to recognize the start of the sector. Okay, that's how I know that that's the position of a start of a sector. It contains a special bit pattern. Okay, after that special bit pattern, I have the information about that sector, saying that I am cylinder number 7 and sector number 15. And at the end of that sector, I have this ECC, error correction code information. So that information is used for, after I read all of this data, after I read all of that data, I compare the calculated ECC number with this ECC number. Okay, I compare the calculated ECC number with this ECC number to see if the data that I am reading is a valid data. If it is not valid, then there is a problem with the sector. Okay, so this is how the initial low level disk formatting is done. Low level disk formatting is done. Okay, there is a high level disk formatting. High level disk formatting has something to do with the file system. It is the placement of the super block and your inodes or the fat table, also your block structure and etc. Okay, so your high level format is very similar to what you did with your midterm project, right? In your midterm project, you formatted your disk depending on your file system. But low level formatting is something to do with the very low level data structure of your desk. Because on your desk there is nothing special that tells the starting and ending positions of the sectors. Okay, so how would I know at what sector I am? I would search for this preamble special bit pattern. Okay, the special bit pattern. What's going on? Okay, I'm going to do this. I will look for this special bit pattern. That special bit pattern will tell me what kind of it will tell me the beginning of a sector. Then after that, I will see the cylinder number and the sector number. Okay. So when you let me open up my computer. Where is my okay? It's my computer, and I have an SSD drive here. When I say format this disk, biçimlendir is the format. Okay. When I say format, I hope it doesn't format it. Okay. Now it says that I cannot format this because you are using it. Do I have any? No, I don't have any. I'm sorry. It would ask you, should I format it fast or slow? Okay. Slow means that format it from the beginning. Format it so that I place all of my sector information, preamble information, and ACC information. If you do fast formatting, that kind of information is left there, okay? You don't write all of them. You only place your file system, empty file system, on your low-level formatted task. Okay, good. Any questions with disk formatting? Okay. So when you disk format, it is up to you. It is up to the operating system. It is up to the disk formatter to name your sector numbers. For example, if this is the rotation of my disk, if this is the direction of the rotation of my disk, these could be the numbers. Number 0, track number 1, cylinder number 1, number 0, number 1, number 2, number 3, number 4. It goes like that. When I go to track number 2, number 0 is here. So number zeros are here, 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 and there. Okay. They do this kind of structure because, let's say I am reading my data sequentially. Okay. I am reading my data sequentially. I read, okay, my disk is rotating this way. My disk is rotating this way. I know that. Okay. Let's say I read the inner track. Okay. I read 0, 1, 2, 3, 4, up to 31. After I read 31, I like to continue reading. Okay. So I need to move my head. Let's say my head is here. Okay. This is my disk arm. My head is here. I need to move my head to the upper track. When I move my head to the upper track, I know that the disk continues spinning, right? The disk spins very, very fast. Arm movement is not that fast. So when I move my head, read write head, from one track to the other track, I know that the disk will keep spinning. So if the disk spins this much, 1, 2, 3, 4 sectors, okay, then I am at the perfect position to start reading the upper track. Okay. So that's why they do this kind of cylinder skew. This is called cylinder skew. Okay. So this is done in a way that when you are doing sequential reading, okay, when you are doing sequential reading, it considers the time that passes when you move your head from one track to the other track. I know that there will be some time passing, and to compensate that time, I format my disk in a skewed way, cylinder skewed way. Okay, so the book has a good example on it. Okay, the amount of cylinder skew depends on the dry geometry, of course. For example, at 10,000 RPM, drive rotates in 6 milliseconds. Okay, one complete rotation is 6 milliseconds. Okay, that's fast. So if a track contains 300 sectors, then in that case, 6 milliseconds over 300 means that for every sector, the read-write head needs 20 microseconds. Okay, 20 microseconds. So every sector needs that much. If the track-to-track arm speed is 800 microseconds, then that means that 40 sectors will pass under my read-write head when I move my read-write head from one track to the another track. Okay, that will be 40 sectors. So in this case, when I do the low level formatting, maybe my skew amount should be 40 sectors. So in this case, my skew amount is 1, 2, 3. Okay. In that case, it says that it should be 40. Okay. So that's the calculation. When you do the disk formatting, as I said before, it is up to you how you are gonna number your sectors, and your drive speed, okay, your rotation time, your track to track, cylinder seek time, speeds are the important factors to calculate this skew amount. Okay, any questions about cylinder skew? Any questions about cylinder skew? Okay, if there are no questions, maybe I should, oh, I did not. I should stop here for 10 minutes of break. Then after the break, we will continue. Okay, 10 minutes of break.
Yeniden bilirim Gebze'yi. Yok. Bayram için almıştık da. Seyyar hocam gelen gider.
Bayram peçelerini de atıyorsun.
Evet.
Maskeyle dolaşıyordum şimdi maskesiz çıktım valla unuttum.
Aynen ben.
Ben de geldim mesela unuttum ama
Tamam.
alabilir miyim?
Tabii sizi alın. Ben de geçeyim.
Tamam teşekkür ederim. Sağ olun.
Hocam kolonya vereyim mi?
Kolonya yok, sağ ol ya, sesin biraz önce. Fazla sıkınca başım dönmeye başladı o bize.
Sabun da şey.
Tamam, şu dersi bitirince konuşalım seninle. Okay, people, let's continue. So we talked about the skew. Okay, again, the skew is going to be calculated depending on the RPM value and depending on the track-to-track seek times. These are the two variables. Look at the skew. By the way, I have a hard drive. Usually I bring this hard drive to class and show everybody how the hard drive works. I'm not sure if I can. Is this how? Okay, yeah, okay, you see it, right? Okay, this is the hard drive. Again, this is the spinning disk. So this rotates very, very fast. And this is the arm that moves in and out, right? Like that. In and out. So this is track number 0, cylinder number 0, and this is cylinder number something. I don't know, it's a very large number. It looks like with this disk, I have only a single platter. I don't see any platters underneath. I have a single platter. So I have two tracks on a single cylinder. Okay. So these kind of disks are common. I mean, if you have a non-functioning disk, just open it up and just check how the internals are working. Okay, so Talai homework number 3 is coming today. So skew amount is calculated that way. Another thing related to low-level formatting is interleaving. Okay, interleaving. Usually, this is the structure of our disk. Okay. Sector number 0, sector number 1, sector number 2, and sector number 3. Let's say I read sector number 0. I have to process it, and after that I am going to read sector number 1. But while I am processing this sector, sector number 1 will be gone under my head, and now I am looking at sector number 2. So I have to wait for the whole rotation of the desk, for the whole rotation of the desk, to read sector number 1 again. So just to let my CPU or my driver to do these kind of calculations, usually I format my low level sectors this way. Okay, I make let's say this is sector number 0, 1, 2, 3. This is no interleaving. I do it in an interleave way. 0, 1, 2, 3, 4, 5, 6, and 7. So there is only one. There is only one sector difference between these two. Okay, so I read sector number 0 while I am calculating stuff, calculating the ECC, doing stuff, transferring the data, filling in the buffers. Then I can the number 4 is under my head. Number 4 is gone now. When I am looking at number 1, now I am ready to read it. Okay, so this is a little bit slow to read because I cannot read the whole track in one rotation. I need 2 rotations, but it is better than waiting for a whole rotation to read another sector. Okay, so this is single interleaving and this is double interleaving. Again, this interleaving depends on your processing speeds, your available buffer space. If you have available buffer space for the whole track, then don't do any processing. Read the whole track. Okay, now you have all track in front of you. Now start processing it later. Okay, because you have the full revolution. When you do the seek, when you move your arm from one track to the another track, then you can do your processing because you will have time in that case. Okay, so interleaving and cylinder skew, they are all related, and they are all related to low level formatting. As I said before, it is up to you how you number your sectors in the low level formatting. Okay, any questions? Any questions about disk level formatting, low level formats? Okay, sometimes I can't see those. It looks like everybody is fine. Okay, so as I said, if you have enough buffer for the whole track, then read the whole track. Otherwise, you are going to use interleaving. Okay, another issue with the disk is the disk arm scheduling algorithms. Okay, let's say I have a disk. With the disk, there are many important factors. The most time-consuming factor is the seek time. Moving your disk head, okay, from one position to another position. Let me see if I can see myself. Yeah, moving your head from one position to another position. Okay, this takes milliseconds of time. Okay, the rotation is very, very fast. So rotational latency is something that we need to be careful about, but disk arm movement is much slower. So when I am as a driver, okay, as a disk driver, if somebody tells me that I need this data and another process says that I need this data and that data, let's say I have many data requests, it is important to schedule them. Okay, if you schedule them randomly, your disk performance will be bad. You need to do it in a smart way. You need in a way that your seek time is the lowest. Okay, you don't want to keep your head moving all around the desk. Okay, so we need to be careful about it. So there are important things are seek time to move your arm from one cylinder to another one, and you have your rotational delay. Okay, rotational delay, you need to wait until your sector is ready under your head, and the actual transfer time is, you cannot do anything about this actual transfer time. It has to happen, and most of the time, as we said before, the seek time dominates the rest of the latencies. Seek time is the most important. We need to optimize it. Let's say I have a desk with 40 cylinders. Okay. Let's say it's like this. I have a desk. Okay. And there are track number 0 to track number 40. Okay, like that. Okay, and this is track number 1, and this is the track number 40. Okay, and I numbered it that way, and there are many processes. They want to transfer data, write or read from the desk, and they say that they need information from track number 1, track number 36, 16, 34, 9, and 12. Okay. These are the requests that they are waiting in a queue. If I use first come, first served strategy algorithm, then I say that, let's say initially I am track number 11. Okay. I am at track number 11. Let's say I am currently here, track number 11. Then I need to move my head to track number 10. Okay. No. Okay. I am at track number 11. Then I need to first move my track number to track number 1. Then track number 36. Then 16, 34, 9, and 12. So moving from 1 to 36 takes lots of time because you are moving the whole range of your cylinders. It's going to take lots of seeking time. Okay, so if you do the first time, first come, you need to move from 11 to 1. That will take 10 milliseconds. From 1 to 36, that will take 35 cylinders. Okay, and from 36 to 16, that will take 20, and 16 to 34, 18, 34 to 9, 25, then 9 to 12 is 3. Okay, so the total of travel time is 111 cylinders. Let's, for the sake of examples, let's take each cylinder takes a single millisecond. It's going to be 111 milliseconds total time. Can we do it better? I mean, if I play with the orders of these numbers, can I do it better? Instead of doing first come, first served, maybe I can do better. There are some other algorithms. For example, the second algorithm that we are going to look at is shortest seek first. Okay, shortest seek first. Okay, as I said before, I am at track number 11, and I will sequence my disk accesses in a way that whichever is shortest, I am going to go there first. So 12 is the shortest, then 9, then 16, then 1, then 36, then 36, 34, and 36. Okay, so this is shortest seek first algorithm. So if I do this from 11 to 12, I need to move 1 cylinders. 12 to 9, 3. Okay, 90 is 16 is 7. 16 to 1 is 15. 1 to 34 is 33. And 34 to 36 is 2. Total is 61 milliseconds versus 111. So 61 is shortest seek time first. Okay, and 111 is the first come, first served. So it looks like if I change my scheduling algorithm, I am saving 60 milliseconds. That's a very, very large time, very, very long time for a computer environment. Okay, so if my driver is operating system, disk management software is smart, knows the disk structure, and whenever it receives requests like that, it makes this kind of rearrangement. Okay, it makes this kind of rearrangement, then my total access times will be much shorter. Okay, so there is a nice graph in the book. The book says that, okay, I am at 11 first. Okay, I am at 11. First, I move to 12. Sorry, I am at 11. I think this is a little bit shifted, right? From 11 to 12, then 9, then I think 16, then 1, and then 34 and 36. Okay, so this is the total time of travel. This is the total time of travel. This is 61 cylinders. Shortest seek first. Another alternative is this. Okay, we say that disk arm is like an elevator. Okay, let's say I have a building, very large building. Okay, and there is an elevator in the large building. Let's say this this building has 100. There are 100 levels. Okay, in my apartment. Okay, and there is an elevator going up and down. This elevator goes up and down. So this looks like a cylinder head, read-write head, the elevator. Whoever is making a call, the elevator is trying to serve them. But it looks like if there are many people inside this apartment, 100-story apartment, okay, 100-story apartment, then it looks like my elevator is going to spend most of its time around the central region, because whoever is closest will be around the middle, and the people at the end of the apartment will not get served much. Okay, because there will be somebody else closer to the elevator. Okay, so the elevator algorithm says this. What I am going to do is my elevator is going to go up or down. Okay, my elevator is going to up or down. It will go up until it meets all the drive request, read-write request in the up direction. Then it will go down until it meets all the read-write requests in the down direction. Okay, that's called the elevator algorithm. So let's look at this. A heavily loaded disk, the arm will tend to stay in the middle of the disk most of the time. If you do the shortest seek first, that's what's going to happen. With the elevator algorithm, there are two directions, up and down. Elevator is either going up or down. Okay, it goes up until it hits the top of the building. It goes down until it hits the bottom of the building. When a request finishes, if it is up, the arm or cabin is moved to the next highest pending request. Okay, if there are no pending requests from the up direction, then I can switch to down. Okay, so this way I am both efficient. It's like shortest seek first, but it pays attention to up and down directions too. So in our previous case, it starts from 11, then it goes to 12, it goes up, then 16, then 34 and 36, then it goes down to 9 and 1, and total of 60 cylinder movements. Okay, in this case I had 111 cylinders for the first come first served, 61 for the shortest seek first, and 60 for the elevator algorithm. Okay, elevator algorithm does not perform better than the shortest seek first all the time, but it is fairer because it gives chance to the end tracks, track number 0 and track number 36, much better chance of getting served. Okay, I have a question. Is the scheduling algorithm in the kernel side, so the scheduling behavior may differ in different operating systems? Well, this disk arm scheduling, of course, it depends on the number of cylinders, right? Number of cylinders and the seek times of your hard drives. Okay, so part of it is very dependent on the driver. Okay, part of it is very dependent on the hard disk, but most of the time these kind of things can be parameterized. So these kind of algorithms are very portable. All you need to do is you just enter the number of cylinders to this algorithm, and you just enter the seek times between the two tracks and etc. And the algorithm will perform very nicely. So this is a very portable algorithm. All of them, first come first served, shortest seek time, okay, and elevator algorithm. They are all pretty much portable. Of course, they need parameters that would explain your hardware. Okay, so these are the disk algorithms. Any questions? Okay, so we looked at three of them, and they are kind of complement each other. I mean, first come first served is simple. You don't schedule anything. For both elevator algorithm and the shortest seek time, you need to rearrange your disk requests. Of course, I assume that all the requests are ready at the beginning, and this is not very realistic. Usually, while you are serving, you get more disk requests, and you get more requests, and with these requests, you can change your scheduling on the fly. An elevator algorithm is more suitable for that one, I guess. Okay, if there are no questions, then I would continue. And again, I will stress this. I need to stress this out. All of these algorithms are for the mechanical disks, like this one. But these are all going away. Instead, what we have the solid state drives. With the solid state drives, there are no seek times, there are no rotation times. Okay, of course there are data transfer times. If I go to the slide again, okay, there are no seek times, there are no rotational delays. Okay, there are actual data transfer times. Okay, for the SSDs. Okay, I have only this, but this elevator algorithm or the shortest seek doesn't apply to SSDs, and interleaving or the cylinder skew they don't apply to disks. Okay, so even low level formatting, there are no sectors on an SSD. So most of these kind of discussions are not valid for SSDs. SSDs, they have their own problems. The most important problem for the SSD is this. Okay, what is the most important problem regarding the SSD handling? Do you know? Does anybody know? It looks like SSDs, they don't have any of these problems, but they have their own problems. Do you know what that problem is with the SSDs? Regarding the usage of the SSD in terms of operating systems? Yes, exactly. Just tell me a little bit more. Max write amount, max write count, or maybe it will take time for you to write it. With the SSDs, let's say this is your SSD. Okay, it's a solid drive. So you have it's a linear space actually. It's like a memory, right? Very large space from byte number 0 to, let's say, 1 terabyte of space. Okay, you get to write only maybe at most 1,000 times to a single position. More than 1,000 times, okay, more than 1,000 times, the SSD starts wearing out. So if I am writing and reading from this position, I can do that only at most 1,000 times. After that, After that, this place of the SSD starts wearing out and it will malfunction. So it is the task of the operating system or the driver of the SSD to make sure that you don't keep writing to the same position in your SSD. Write to different positions. Okay. For example, if you have a array that you keep accessing at the beginning of the disk, from time to time you should move this array to some other positions of the SSD drive. Okay. So we don't have this kind of a problem with the mechanical hard drives. I can write as many times as I like to the same position. It should not make any difference. But for the SSDs, it is different. For the SSDs, it is different. You cannot keep writing to the same position while not using the other parts of the disk. Okay. So yeah, Kamil, so either the operating system has to do it or the driver that comes with the SSD has to do it. Okay, so it chooses the random. So there is a virtual mapping going on the SSD. For the operating system side, it always operating system says that, okay, address number 0 is here, address number 1 is address number 1 terabyte is here. Operating system knows that, but it is up to the SSD driver to make this address a virtual address and keep changing the physical position of the data. The operating system or the user thinks that it is writing to the same position. But remember, when we use the virtual memory, I don't know, as a user, I don't know what kind of, what part of the memory I am writing to physically, right? So it depends on my virtual memory table. Okay, so usually it is the task of the SSD driver to make sure that it is using the all SSD space evenly using some kind of a virtual memory technique. So but we are not going to talk about, okay, I'm not trying to tell you all the details about SSDs, but SSDs are not problem free. Okay, SSDs are not problem free. They have their own problems, and their problems are different than mechanical hard drive problems. And it looks like they are going to solve this maximum amount write problem by making some progress on the solid state drives, but the still problem, we have this kind of problem there. Yasin, what you are saying is correct. Beside the free space tracking and the virtual addressing, it needs the write counts as well. Yeah. So it looks like they are keeping some kind of a virtual address table, and in virtual address table they keep how many times I have written to that position. Okay, so when you buy an SSD drive, they usually tell you how many times you write to that SSD drive. Let me try to find it. SSD max write times. So let me try to. So somebody was doing this experiment, reading and writing and reading and writing to the SSD. Okay, it says that it changes between 3,000 to 100 times. Okay. The cell forgets new data. So let's see. They didn't give any specific numbers for. Oh, okay. Long-term test conducted by Germany's most respected somebody. And it is German. Let's translate it. Oh, I think we can understand. What? Choose configure. I don't know what. I think I choose this one. I don't want you. It wants. Oh, okay. It wants me to turn off my ad blocker. Ah, yes. Let me see if I can. I couldn't find it. Anyway, you learn German first and you read this later. And usually the SSD drive manufacturers, they publish. Okay, so it is, looked it up. My 120 gig SSD says that it can write. Oh, okay. So 75 terabytes for a 100 gig. So that means that it is 750, right? 750 times. Okay. So it is around, yeah, so maybe 5 times, 6 times, 6 times, 10 times, let's say it is 100 gigabytes. Okay, 625 times. We don't have these kind of numbers for the hard drives. Hard drives, they can operate. There are some hard drives that have been running for the last 40 years. That's really, I mean, they are that reliable. And in fact, I don't know what kind of storage they had on the space crafts that they sent in 1970s. I mean, are they using hard drives on that? I don't think so. No, I think they are using solid state drives. What kind of secondary storage do they have on Pioneer? Oh, it Pioneer spacecraft. Okay. I don't think that I'm going to find that information very, because in 1970s that small hard drives were not that. I think they are keeping everything in the main memory. Maybe the Mars rovers. Okay, you can look it up, and we're gonna see if HDDs had multi-function. We can use the what? I don't know what you mean by that, Kamil. Magnetic disks are HDDs. Oh, you mean that the head is broken? You mean that this read-write head, this head is broken, and you are saying that just take the head out and use the disk. But usually this is the problem. When the head is broken, okay, it malfunctions, it is bent, and it usually touches the surface. When it is touches the surface, when the surface is spinning like 10,000 RPMs, it messes up all the surface. So it is not easy to make that. Repair. Okay, anyway, so let's go back to our slides. As I said before, these are decades of algorithms, and it looks like they are going away with the hard disks. But remember our golden rule of the operating system. Okay, if you have invented something, there is a good possibility that you're gonna use it later, maybe after 10 years later. It will come back again. Okay, we looked at the disk arm scheduling algorithms, and okay, for the error handling, remember we said that it is the task of the IO software to do the error handling. It has to be transparent to the user. Let's look at this error handling of the bad sectors. Let's say that I have a bad sector at number 7 on a single track. Okay, how do I understand the first question? How do I understand that sector number 7 is bad? Question: how do I understand that if the sector number 7 is bad? How do I know that? Bad sector means that it doesn't hold my data. No preamble information. If there are no preamble information, then your low level formatting is bad. It is not a sector. It's not a sector problem. Your whole disk is messed up. Your whole disk is messed up. So that's a much more serious problem than a single sector, Yasin. But you are close. Instead of using the preamble, use the ECC information. Remember, in a single sector, at the beginning I have the preamble and I have ECC. I have the preamble and I have the ECC. What is ECC? Error correction code. Okay. You read the data from the sector, you calculate your ECC, you read your ECC from the sector and compare them. If they are different, that means that the data that you had written and that you are reading are different. So if this is the case, you rewrite your data to see if the ECC are matching. No. And that means that that sector is bad. It doesn't hold the data. Why is that sector bad? We don't know. Maybe it's a manufacturing problem. Okay. Even straight from the factory, brand new hard drives, they may have bad sectors, and those bad sectors has to be marked. Okay. And during the lifetime of the disk, that you may have more than many more bad sectors, and they all have to be handled. So this is what we do. We keep spare sectors at the end of each track. At the beginning, these are not used. Okay, we don't use them. These are all empty. So I have total of 30 sectors on a single track, but I have place for 32. So if a sector goes bad on a single track, I can maybe do this. Place the sector number 7 here. Okay. So the when you read it, when you read this part, the preamble says that I am a bad sector, 7 is not here, and when you read this part, it says that I am number 7. Okay. Or I could do this. I could shift all the sectors one position over, and I can do this. Okay, so this is one way of handling the bad sectors. Of course, these are again for the hard disks. This is not valid for the SSDs. Okay, SSDs. And each solution has a. I mean, this is definitely better solution for sequential reading, because after 6 there is 7. Okay, but in this case you have to shift. You have to rewrite all of your data. So fixing this is expensive. This one is slow in terms of sequential reading. After 6, you need to make a whole rotation to get the 7, then another half rotation to get the 8. Okay. Good. Okay, any questions? And by the way, when you move your head to a new cylinder, okay, you start reading your data from that cylinder. You read your sector's preamble, and the preamble says that I am cylinder number 17 and sector number 15. Okay, and if what you are reading and what you are thinking is not the same, then you are in the wrong place. Okay, your arm is in the wrong place. It can happen because this is a mechanical stuff, right? This is mechanical. Okay, when you do this, it just moves. Okay, when you shake it, it moves like that. Okay, so this is all mechanical. it can from time to time may go out of calibration. You need to recalibrate again. From time to time, your driver moves this head to the track number 0 like that, and then says that, okay, I'm going to count the cylinders one by one now. Okay, so that's what is done by the driver of the hard disk, and it causes some delay when I do the reading. Okay, that's why people say that for real-time systems, never use hard disks. Okay, because hard disk may stop responding to your request because they might need to do the calibration again. Okay, so for the real-time systems, we don't use any hard disks. Okay, good. So I will skip this part. Should I skip this part? Maybe I should not. No, okay. Let's look at this concept too, stable storage, because this is important. We looked at RAID. RAID is good. RAID is good for speed. RAID is good for reliability, right? If my system crashes, okay, if my system crashes, I can recover the data, crashed hard disk data from the other disk. We know that. But RAID has a problem. Okay, let's say I am writing some data to my disk, and while I am writing the data, the disk has crashed. Okay, or the system has crashed. Okay, so I wrote half of my data to the disk, half of them is not written, so my disk will be in a inconsistent state. It does not matter if the system is a RAID system or not, because while I am writing to the RAID system, in the middle of the process, if my CPU crashes, my operating system crashes, I don't want to be in an unstable state. So they developed a solution called stable storage. It works like this. Okay, you write the same data to different disks, one after the other. Okay, so first you write your data here, then you write data there, the same data. If the crash happens before you write any of the data, then you have your old information in a consistent state. If the crash happens when you are writing the data to the first disk, okay, this disk will be in an inconsistent state, but I have my data, the old data, in the second disk. If the crash happens here, both of them are consistent, but this is old data and new data. You may either copy here, there, or there to there. Okay, it doesn't matter. If crash happens here while I'm writing that one, I have my new data in the old one. Okay, so this is the case. This is called stable storage, and the idea of stable storage is write your data to different disks, one after the other, not at the same time, but one after the other, not at the same time. So this means that your writes will be slower. Yeah, that's true. Your writes will be slower, but your storage will be much more stable than the alternatives. So there are stable writes, stable reads, and crash recovery. For the reads, there is no problem. Reads are as fast as before because you just read it from the first disk. For the writes, you need to write it 2 times. Okay, for the writes, you need to write it 2 times. So this is a little bit expensive. Like the RAID, it uses more than 1 disk. But the whole idea of using more than 1 disk is not because of the speed. It is because of the stability. Okay, stability. Stability is different from redundancy. Okay, in the RAID, I have more than 1 disk, and if there is a disk crash, if one of the disks are crashing, then I can recover my information. This one doesn't say that. This one says that I will always keep a stable copy of your data either in the first drive, on the second drive. That's what it says, which could be very important from time to time. Okay, good. Any questions? Okay, if there are no questions, I will look at the one of the other important I/O devices, which is the clock. Okay, clock is an I/O device. It's a very special device, but it's a very important one. Okay, I need this clock device. It is connected to the, of course, system, and it has its own driver, and I can make system calls that uses the clock hardware. And the most important task for the clocks is maintaining the time of the day. I need this information because I need to show the time information to the user. I need to use this information in my file processing and etc. Right? And also I need this clock so that it produces a interrupt. If some of the processes are running too long, it produces an interrupt. My CPU is interrupted. I can switch from that process to another process. Also, to calculate the CPU usage time for the different processes, I am going to use the clock again. And sometimes users, they say that, okay, this function called sleep 3000. Sleep 3000 means that wake me up. I am going to be blocked. I am giving up the CPU. Wake me up in 3 seconds, 3000 milliseconds. Okay, so the clock is responsible to make sure that this process is running again after 3 seconds. So handling alarm system call from the user processes. Also, we will look at this nice concept, watchdog timers. They need the clock hardware. And then again, for profiling, monitoring statistics for the whole system, we need the clock. So we are going to look at the clock hardware first, and we are going to look at the clock software. Let's look at the clock hardware. Okay. Previously, in 1950s, clock hardware was like this. Remember our main power source, city power, is alternating current. Okay, is like a sine wave. Okay, it goes from a negative number to positive number, negative number to positive number, and in USA usually its amplitude is 110 volts. In Europe it is 220 volts, and in USA it is 50 hertz. So the frequency of this power cycle is 50 hertz for USA, 60 hertz for Europe and Turkey. Okay, so they know that the computer is connected to the power, city power, right? So I have this nice sine wave. If I produce an interrupt at the top of these positions of the input power, then that means that 50 times a second I can produce an interrupt, right? So clock is as simple as this. Every 50 times a second, 1/50th of a second, I will get an interrupt at this position. When I get that interrupt, okay, I will increment a counter, okay? So that counter is incremented 50 times a second, and I will make count of those interrupts. So whenever I need to calculate the time, I divide that number by 50 to get the number of seconds, right? Since the start of the system. Okay, that was the idea, but we are not using this one for nowadays. Instead, we have this hardware structure. This is not that good. Instead, we have this hardware structure. Okay. In our hardware, we have three things: a crystal oscillator, a counter, and a holding register. Okay, this is the crystal oscillator. Okay, this crystal oscillator is special. It's an electronic device. Okay, it produces a pulse at a very, very precise time interval. It's very, very sensitive. At a very, very precise interval, it produces a pulse. Okay, that crystal is properly cut. It can be made to generate a periodic signal at a very great accuracy. This signal is fed into a counter to make it count down to 0. When the counter gets to 0, it causes a CPU interrupt. Let's say this is my counter. Let's say at the beginning, this number is 1, 1, 1, 1, 1, 1. It is all ones. Okay. Every time this one produces a pulse, I will decrement this by 1. So it became 1, 0. Then another pulse, it will become 0, 1. Another pulse, it will become 0. Okay, so when this number reaches number 0, okay, it produces a CPU interrupt. Okay, it produces a CPU interrupt. So now CPU knows that there is a certain amount of time has passed. Okay, a clock interrupt has occurred, and it handles the clock interrupt, and it copies this number, whatever that number is, to this position again. So this one starts counting from the beginning. So this is called holding register. It's one constant number. Okay, every time this one becomes 0, it causes an interrupt. And after the interrupt is handled, this number is copied again to this position. Okay, so this is how the hardware side of the clock works. This is simple. This is much simpler than hard disk, of course, but it is as important as a hard disk. And we will see how the software for this clock works. Okay, but it looks like I'm out of time. Then on Monday we will start talking about this. I was hoping to finish up with this chapter, but I think I will finish up with this chapter on Monday. And also I will start talking about the deadlocks on Monday and Tuesday. We will finish up with the whole semester then. Okay, and your homework will be coming today. Okay, any questions about today's lecture? Any questions? Well, if there are no questions, then that's it for today. Thank you, and see you on Monday.